Hello, welcome to this video on base E functions. Today we're going to go ahead and look at modeling with base E, introduce you to the number E, and then go ahead and look at some contextual applications. Before we go ahead and get started, just a refresher, what values of bases and exponential functions produce growth or decay? Hopefully you answered exponential growth occurs with a base that's bigger than 1. If you're multiplying by something with a value bigger than 1, it's going to grow. And a value less than 1 is going to produce exponential decay. All right, let's go ahead and talk about the number E. E is a number, and it is an irrational number, similar to pi. How pi is 3.141592653. That's all I got. E is sometimes called the natural base and is used extensively in scientific and other applications of exponential growth and decay. E is approximately 2.7. 2.718 if you want to get real fancy with it, but approximately 2.7. Okay, and then here's a graph of y is equal to e to the power of x. Okay, let's go ahead and look at some applications that contain base E. Here we have the Dow Jones index is a stock market index for the New York Stock Exchange. The Dow Jones index for the period of 1980 to 2000 can be modeled by the function V of dj of t is equal to 878 e to the power of 0.121 times t, where t is the number of years after 1980. Okay, so in this case, they already gave us the function, and then part A here, they say use the function to estimate the Dow Jones in 1989. So in this case, we need to figure out, okay, what is t? What am I going to plug into my function? Well, this function is modeling 1980 to 2000. So if 1989 is our year, I'm going to go ahead and subtract 1980, and our t value is 9. So I want to evaluate this function, v subscript dj. That's just more of a notation to tell you what specific value they're talking about. And I'm going to evaluate the function at 9. So v of 9 is equal to 878 times e to the power of 0.121 times 9. Okay, and so we're going to go ahead and plug this into our calculator. Note here, I'm going to show you the number e. So here is the calculator. E is a secondary function to the natural log. So you'll see it right here. So there's ln, and then you'll see the secondary function is e to the x. Okay, so again, in order to hit e to the x, you're going to hit the second button right here, hit the second, and then hit the ln button, and on the screen you'll see this. It'll say e and then have a little caret with parentheses. Okay, so let's go ahead and plug this into the calculator, and over here I'm just going to show you what your calculator will what it should look like, because I can't show you on screen here. So I'm going to have 878 times, and I'm going to go ahead and hit E, and you should get something that looks like this. And then I'm going to multiply times 0.121 times 9, and then I'm going to close that. You want to make sure you have parentheses around whatever's in your exponent to protect that, okay? So we're going to go ahead and compute this. 878 times E. Okay, and I get approximately 2,608.80. Okay, so we can say the Dow Jones was about 2,608.80 cents in 1989. All right. Next question says use the function to estimate the Dow Jones index in 1992. So again, I have to go ahead and I have to take 1992 and I'm going to subtract 1980, which gives me 12. Okay, so I'm going to go ahead, I'm going to reuse this same function. And here's a trick on your calculator. If I want to reuse what I had, I'm going to go up here and I'm just going to go ahead and I believe it is, if you hit the up button, you'll re-access it. Or if you just hit, oh, that's my calculator, sorry. Just hit the up button and then you can edit the exponent in it. Okay, so we'll go ahead and do this and we'll enter it at 12. And we get 3,750. So V of 12 is about 3,750.51. Okay, and so we'll say that here. The Dow Jones was about 3,750 and 51 cents in 1992. Okay, here is the second example. And in this example, we are given another context about a base E formula. So here it says paleontologists study fossils and can determine their age using the natural decay rate of carbon-14, where the age of a fossil is the number of years following the death of a specimen. The percent of original carbon-14 in a specimen T years after the death of the specimen can be modeled by the function n of t, which is equal to 100 e to the power of negative 0.12 t, where t is the number of years after the specimen died in thousands. In thousands. And that's very, very important. We'll talk about that here in a second. So they say here, determine the percentage of carbon-14 in a specimen that has died, or that died, should be no was there, that died 15,000 years ago to 3 decimal places. So since the specimen died 15,000 years ago, I'm going to take 15,000 and we're going to divide by 1,000 because t is in thousands. So when I divide 15,000 by 1,000, we get 15. So when I plug in 15, it's understood that the specimen died 15,000 years ago. Okay, so here is our equation. So n of 15 is equal to 100 e to the power of negative 0.12 times 15. Okay, and so we'll go ahead and plug that into our calculator. Okay, and we get 16.529, but if we round, that's going to be 530. Okay, so there's our answer. So if a specimen died 15,000 years ago, there will be about 16.530% carbon-14 left. All right, example number 2. Determine the percentage of carbon-14 in a specimen that was died 10,500 years ago. That died 10,500 years ago to 3 decimal places. Okay, so again, we're going to take 10,500 and we're going to divide by 1,000, which gives us 10.5. Okay, so again, I'm going to plug this into our function. N of 10.5 is 100 e to the power of negative 0.12 times 10.5. Okay, so we'll plug that in. and we get approximately 28.365. Okay, so there will be about 28.365% carbon 14 left in a specimen that died 10,500 years ago. Okay. All right, I do have some practice problems for you here. So here is a problem. Please go ahead, pause the video, and then you're going to estimate. Here they're talking about the, I think it's called the Nikkei 225 index, a stock market index for the Tokyo Stock Exchange. Find out how much it was valued at in 1998 and in 2000. Go ahead, pause the video, and I'll have the answers here for you in a second. All right, so here are the solutions. Since the function models the period 1990 to 2010, you're going to calculate t. Those are the years after 1990. So t for 1998 is going to be 8. And so we evaluate that. And here it looks like they wanted the nearest whole number. If you had the decimals, I think that's fine. Unless they said round to a nearest whole number. And then in 2000, your t value is going to be 10. So 16,055. Okay. Next example. Here it says the amount of sodium-22 present at a time t in years can be modeled by the function s of t is equal to a times e to the power of negative 0.267 t. They say if 300 grams of sodium-22 was present in a soil sample in 2010, how much sodium-22 will remain in 2020? Round to 3 decimal places. So one thing that they do with this function is they leave out the initial value, the a value, but they give it to us in the question stem. So here the initial amount is 300 grams. So 300 grams. Okay, so our function is going to be s of t is equal to 300 e to the power of negative 0.267 t. Okay, so they say this was in 2010 when there was 300 grams. So then our t value, if we want to find out how much will remain in 2020, we're going to go ahead and subtract. So 2020 minus 2010, and that is 10 years. So I'm going to go ahead and evaluate s at 10. So 300 times e to the power of negative 0.267 times 10. Okay, and we get approximately 20.7756. And they want us to round to 3 decimal places. Okay, so we can say in 2020, I don't know why I can't write 2020. In 2020, there will be about 20.776 grams of sodium-22 remaining. Pretty easy. All we have to do, plug it into our calculator and evaluate, and we are good. Okay, here is a practice problem. Please pause the video. They're going to talk to you about the population of a bacteria colony. Okay, hopefully you went ahead and paused the video and gave this one a go. Just a couple of notes if you did get stuck. Here the function, they define b of h as a times e. Same idea again, just from our last lesson. A That's an initial value. And so they tell us if there are 750 bacteria when the scientists first count the colony at noon, so there's your A value. A is 750. So 750 times e to the power of 0.2357 times h. The other curveball in this problem is that our independent variable, what we're plugging in, we have to plug in an h value that kind of adheres to what they say. And here it was very straightforward because they say the scientists count the colony at noon. How many bacteria will there be at 9 p.m.? So that means that 9 hours has passed. So we're going to evaluate B at 9. Okay. And this gives us about 6,256 bacteria. All right, for closure, go ahead, please discuss the similarities and differences between the irrational numbers e and pi. Alrighty, hopefully you came up with a couple. Here are some of the similarities and differences that I just quickly brainstormed. Similarities, they're both irrational numbers, and they both have special characters with their own button on a calculator, and they both represent numbers. They're both numbers. Some differences, though, are that they do have different symbols. One's a letter, and then one's a Greek letter. Pi is used in circular applications, and e is used in exponential applications. All right, that's going to do it for this video. Hopefully you learned about the number e and how it is used to compute and model exponential models. All right, catch you in the next video. Peace.